All right, hello. In this lecture, as well as really the next three lectures after this, basically what I'm going to try and do is cover some of the concepts from physical chemistry that are going to be important as we move into our study of reaction mechanisms, and particularly reactions at the molecular level and constructing the rate constant. So this, and here I'm assuming that you might not have had a physical chemistry course, or maybe you're taking it simultaneously, or maybe there was a lot to physical chemistry, so maybe it's helpful here to kind of zoom in on the things that are going to be most important for the further lectures in this course. Okay, so first of all, some references. I've been using the Macquarie physical chemistry book to develop most of this content, as well as some other references. For example, this one here from Khan Academy. Okay, so I'm going to start. Like I said, there's four of these lectures. Three I call PChem Crash Course, and the last one I call linking the PChem Crash Course back to kinetics. And each one of these are going to have different topics. If you feel comfortable with one of these topics, you don't need to maybe dive into these videos, but they're here if you want them. So in this lecture, we're going to review some of the essentials of quantum mechanics, and we're going to do this in a way that, or we're going to look at the pieces of quantum mechanics that are going to become useful for our future lectures in chemical reaction engineering. I'm going to take a more theoretical approach to doing this. So there's kind of two schools of thought on how to teach quantum mechanics. One of those is to teach the math and how all of the, for example, wave functions are developed. Another one is to kind of talk about it theoretically and try and relate it to the classical world. So I'm going to take this second approach. The reason for that is actually I use quantum mechanics in my research, and I know that a computer is going to do all the math for me, so I don't really worry too much about the math as much as I do understanding or being able to predict what answers I should get, and knowing if the answers the computer gives me are reasonable. Okay, so a lot of quantum mechanics lectures start with a history of quantum mechanics. I'm not going to dive too deeply into that, but I do think it's important. Quantum mechanics was a disruptive theory. So it basically came about due to the fact that there were observations being made that could not be explained using classical mechanics. So classical mechanics is essentially the observable world, what we are used to observing. Classical theory essentially means Newton's equations of motion. Also the Maxwell equations, I believe, for electrostatics, electromagnetism. I don't know exactly, and I may be getting this Maxwell piece wrong. But basically, in classical mechanics, it's that things happen on a continuum. So a main difference between classical mechanics and quantum mechanics is that in classical mechanics, all values, or we'll say any value, is possible. Functions are continuous. Actually, and let's not say functions, let's say energies are continuous. So you think about if I drop my pencil, which I'm not going to do because I'm afraid it will break, but if I were to drop it, its potential energy as it falls to the ground is going to be decreasing, and its kinetic energy is going to be increasing, and that happens in a continuous fashion. Whereas in quantum mechanics, only certain values are possible. So if you think about, for example, the energy levels within an atom, the energy levels for the electrons within an atom, there's only certain possible values, right? An electron doesn't have a continuous energy range. It's either in 1s or 2s or 3s or 2p, and all of those have different energies, but there's no continuum. There's no room or space in between 1s and 2s, for example. You're either in one or the other. So energies are discrete, and I don't know if I'm spelling, if that's the right discrete, you know, you know what I mean. So there's, they're discretized, they're quantized. So as quantum mechanics is being discovered, this is kind of what's going on. So people are observing, they're doing experiments and observing energies that aren't continuous. So one of those is heat and light and non-reflective surfaces. So an example of this is going to be like a stovetop burner. So I have a picture here. So there's maybe metal in this, maybe the stovetop burner is made of metal, and you turn on the stove and that supplies heat to the stovetop burner and the metal turns red. So as it's doing that, it's also emitting heat. So it emits both heat and light. The heat cooks the food, the light is just emitted. So this is a quantum phenomenon. What classical theory predicts is that as you increase the heat on the burner, that the light that's emitted should continuously become higher in energy. So by higher in energy, it should go from, you know, red to orange to yellow to green to blue to purple. But it doesn't. We know that if you heat that burner, it just stays red. And that's because the heat that's applied is only enough to get it into this red spectrum. So not enough heat is supplied to get the metal to turn a different color. So in reality, the burner turns red. Doesn't continue to change color until more heat is added. So to do that, there would have to be the right amount of heat would need to be added to get that burner to go up to, say, the orange level. And I should note here that the experiment that was being done, this was, you know, at the beginning of the 1900s. This wasn't a stovetop burner. The stovetop burner is just an example I'm giving because it's something that we are probably more familiar with. Another one is the emission spectrum of atoms. This is similar to the stove. So an atom receives energy from some source, that may be heat, that may be light, that excites an electron. So an electron gets promoted from its ground state to an excited state. And then when the electron relaxes back, it emits light. Classical physics predicts that, in fact, let me go back here and do this. Classical physics predicts that up energy, that's input, color, so I guess here I'm saying that up energy input, I should say, what I mean here is that the color that's emitted kind of spans that spectrum. That would be the same thing we would say here, up energy color that's emitted should span this spectrum, and it should happen continuously. So as I continue to add energy to this atom, then as it's relaxing, it's having a color spectrum that is concomitantly moving across this color spectrum. Same here. This would be continuous. Sorry for jumping around. It's been since 2019 since I gave this lecture. So in reality, we probably know from general chemistry that what really happens is that atoms give off specific colors of light, and that again, to give off these colors, they must absorb energy in specific quantities. And this is again because you're going to promote this electron. It's either going to be in the next orbital up or back in its original ground state orbital. It's got only two choices. It doesn't, it can't exist in, some space in between, for example, 1s and 2s. There's nothing there. There is only 1s or 2s, right? There's nothing in between them, right? So that's the quantization. So in these two examples, the energies of the light that was emitted in the first one and the electrons in the second one, they are quantized. That means that they can only assume specific, discrete, and again I might be using the wrong discrete, but I mean like the discretized, like separate points, like non-continuous. I don't mean the being secretive one. And I don't even know if I got that second definition correct, so if I didn't, I apologize. Okay, so they can only assume specific discrete energies. Their energies are not so they absorb energy, but the energies that they emit are not continuous functions of that. Okay, so that's quantum. Most of the world that we are observing on a normal basis appears to follow classical mechanics, and that's because we are dealing with things that are, in general, large and hot. So, usually the larger the thing it is and the hotter it is, the more energy levels it has access to, and so its energy levels tend to become continuous. Whereas things that are small or cold, and by cold it depends on the substance, but if we take something like the hydrogen molecule, the difference between hot and cold for the hydrogen molecule, and the hydrogen molecule is a pretty small particle, is like 77 Kelvin, if I remember correctly. So a hydrogen molecule that's hotter than 77 Kelvin is hot for hydrogen, and a hydrogen molecule that is colder than 77 Kelvin is cold. Hence, if you have hydrogen molecules if you have a sample of hydrogen molecules above 77 Kelvin, you can treat them maybe as classical particles. Whereas if you have a sample below 77 Kelvin, maybe you have to treat them as quantum particles. So in general, we are dealing with, if that's our definition, we are dealing in general with things that are large and hot, which means that we are kind of the things we deal with have lots of energy levels. They seem continuous, even though they really are quantized, and henceforth, to us, the world operates on classical mechanics. So when these other types of discoveries are coming on, this is like weird, right? This is like, why is this happening? And the reason is because in reality, quantum mechanics controls everything. So, yeah. Okay, so the energies in quantum mechanics are calculated using the Schrödinger equation or a variation thereof. I'm not going to get too into that, but we probably know what that looks like. That's going to be your H psi equals E psi. H is the Hamiltonian operator. The hat denotes an operator. So an operator operates on a function. So for example, ddx is a operator that operates on a function, takes the derivative with respect to x. The hat denotes that this is going to be an operator, and we'll get into that in a minute. Well, maybe I'll talk about this. This comprises for the intents and purposes of this series of lectures, this comprises kinetic and potential operators. Psi is the wave function. It does not have a hat, it's a function, so it's not an operator, it's a function. It's going to be operated on by the operator. It describes the probability of, I should phrase it a little more technically, finding the particle, and I'll elaborate on what that is in just a minute, in some location. And the location is going to be, location is going to be with respect to the field that's set up by the potential energy operator. So the potential energy operator within the Hamiltonian. E is the energy of the particle corresponding to the specific wave function. So we're going to see that there's going to be many of these, right? If we have discretized energies, that means we have several values of energy, right? They're not continuous. There's several values, but they are going to span, a large range of values. Each one of those is going to have a wave function associated with it. So the energy is telling you, okay, this wave function says, hey, maybe the particle can exist in this region with respect to the potential that's set up by the Hamiltonian, and if it does, this is what its energy is. And so you're going to end up having many of those. I say the particle because the Schrödinger equation can be used to describe any quantum particle. So in this lecture, for example, we are going to use it to describe, we're going to define the particle maybe later in this lecture as the electron within a hydrogen atom. So that electron is the particle. Later, though, in one of the next lectures, we're going to use the Schrödinger equation to describe a sample of helium atoms. So we're going to say a helium atom within a sample. So in that case, the helium atom is going to be the particle. We're going to do the same thing with carbon monoxide molecules. And in that case, we're going to say the carbon monoxide molecule is the particle. I used the example earlier of hydrogen molecules. In that case, the hydrogen molecule was the particle. So really the particle here, it's vague, but it's intentionally vague. It can mean, whatever system you're trying to describe. And so, that's kind of similar to if we think about classical mechanics. If I'm going to drop an object, I can drop my pencil, I can drop my coffee, I can drop my hat, right? So, it's similar. But I think it can be, we're used to understanding that in terms of classical mechanics, in terms of quantum mechanics. That can become more confusing because the particle just seems kind of vague. Okay, so the solutions to H psi, E psi are the wave functions and their associated energy values, where each wave function describes a possible position of the particle in the field of the potential that is defined within the Hamiltonian, and each energy describes the kinetic energy of that particle for that wave function. So the solution is made up of combinations of psi and E. So we talk about the energies of these particles as being quantized. So, but when we observe a system, right, we aren't observing a bunch of discrete energies. So like, what's going on? So if I have, a bunch of atoms, for example, and most of those atoms are in their ground state, but one or two of them is in their excited state. What energy am I observing, right? I can't observe any one atom, right? So I can't look at one atom. I'm observing a sample of atoms. So what am I observing? We are most likely observing the average energy. And I will talk about where that comes from. I will talk about where that comes from in an upcoming lecture. Okay, so I like to start the discussion of, the illustration of H psi equals E psi using the hydrogen atom. That's because that's something that we're familiar with, right? As chemical engineers, that's the thing that we're familiar with. That's a concept that we're familiar with. So I'll get into some of the other common quantum mechanics models in the next lecture as I illustrate their specific uses, but I want to start with the hydrogen atom here. Okay, so the Hamiltonian is going to include, for the hydrogen atom, it's simplest system, so it's going to include two terms. One is going to be the kinetic energy operator, and that's going to be for the electron, so that kinetic energy operator is operating on the electron. Because it is the particle in this problem. And the second one is going to be the potential energy operator, which is due to the interaction between the electron and the proton. So we're looking at a hydrogen atom. It's an isolated hydrogen atom, so it doesn't interact with anything else. It's all by itself. So the electron only really has the opportunity to interact with the proton, and that's where the potential energy is going to come from. So that proton sets up a field, and so the electron has kinetic energy pursuant to that field. We assume that the proton is held fixed, so it does not have a kinetic energy. That's an approximation. It's called Born-Oppenheimer approximation. But the approximation is that since the proton is part of the nucleus, which is significantly more massive than the electron, the proton stays fixed in space, and the electron has kinetic energy that's pursuant to the potential felt that it feels from the proton. Okay, so it's going to have these two operators. The Hamiltonian is going to have these two operators. What the operators are going to do is operate on the wave function. We gave this example before. An example of an operator is a derivative function, or a derivative operator, which operates on some function. So for example, if I took this d dx and I operated it on x squared, the result would be 2x. The operators in the Hamiltonian are similar to this d dx operator, not exactly, but they work in the same way. So this is different than classical energy equations, which involve functions that operate on values. So again, if we go back to potential energy, we can calculate the potential energy of this pencil based on its height above the ground. So I give it a height, and it tells me a potential energy. That's different than what's going on in the Schrödinger equation. In the Schrödinger equation, what happens is I operate on a wave function, and that results in an energy. It also results in a wave function, so it's a little bit different. So for the hydrogen atom, the kinetic energy operator, which I'm going to denote here as a K, that is going to be equal to this quantity here. So in this quantity, this nabla is going to be partial x, partial y, plus partial z. If I take the nabla squared, that's going to be basically the square partials. These have other names, I think, and I've forgotten them because it's been a long time since I've been in a class like that. Other terms, this h bar is Planck's constant divided by 2 pi. ME is the mass of an electron. So this kinetic energy operator here is not identical at all, but analogous to the classical definition of kinetic energy. I'm not going to get into how this came about because I think it's kind of a distraction from where we're going. It's one of these things where we just have to trust that the development of this, and that this answer is correct. Now, if you want to go do research and challenge that, that is absolutely fine, but for our purposes, I'm just going to trust it. Okay, the potential energy, which I'm going to denote as V hat, is due to the field. We'll say the field that's experienced due to the proton. So the electron experiences a field due to the proton, and the reason for this is that these two things are oppositely charged. So the electron's going to feel that in a Coulombic way. And the form of this operator looks like this. In this operator, E is the charge of an electron or proton. We'll say the electron. It gets a negative sign out here. Well, actually, let me say it's squared. That's because we're accounting for both the proton and electron. So we're saying we want to multiply their charges by each other. And so it gets, since they are the same magnitude, it gets squared, and then we have a negative sign out here since they're oppositely charged. Epsilon naught is the vacuum permittivity. This is a constant that you can look up, or if you want to. R, the distance between the proton and the electron. And you see that this equation here is analogous to the classical version, which is basically the Coulomb potential energy. So in this equation, if we want to know the Coulomb potential energy between two charged particles, we take their charges, we multiply them together. That's essentially what we're doing here. And then that's equal to some constant, and then divided by the distance between the two particles. So that is essentially what we've got going on in this potential energy operator. Okay, so the solutions to the Schrödinger equation for the hydrogen atom, they then must satisfy H psi equals E psi. So if we take the Hamiltonian and fill in those terms, this is what we get. So basically what this is saying is if I take partial derivatives, or the second partial derivative of all three dimensions of my function psi, I need to be able to recover that function. So I guess also I need to be able to take that plus and then have this potential energy term there. And if I do that, I need to be able to recover this function. The main issue here, though, is this piece, the derivative. So this basically tells me that when I take these derivatives, I need to recover the same function. So any function that satisfies this condition is valid. So as long as I satisfy that, that's valid, which maybe is confusing to us because we know the solutions to the hydrogen atom. But really any function that satisfies that is valid. I don't want to show how to solve the problem because it's a lot of math, to be honest. It took me taking a graduate course in engineering and science math to be able to appreciate the solutions to this, and I still didn't understand it until many years later, so I want to skip the math. And just let you know that this is a well-known problem that mathematicians have worked on. There is a set of equations called the spherical harmonics that satisfy this requirement. And so I'm just going to trust that. How it works is that they involve sine and cosine functions. The reason that they involve sine and cosine functions is because if you take the second derivative of a sine and cosine function, you recover the sine or cosine function. So that fits within the Schrödinger equation. We could write down the spherical harmonic equations. I don't even want to do that. We could plot them. I've done that before. It's kind of fun. So if you like that sort of thing, I encourage you to do it. If we plotted them, these are the different shapes we would get. So you recognize these as the atomic orbitals. The solution to H psi E psi is essentially, 1s, 2s, 2p, 3s, etc. These various functions. And we'll say, and their associated energies. They represent where the electron can reside within the hydrogen atom and its associated energy levels. So in theory, the hydrogen atom can exist in any of these atomic orbitals. So you have a hydrogen atom. We know that electron is in 1s, but that's just the most likely place where it is. In reality, it can be in any orbital. However, the probability of finding it in any orbital is related to the energy of the orbital relative to the energy of the 1s orbital, and also the temperature of the hydrogen atom. I put temperature in quotes because in reality the hydrogen atom just has to receive energy from some source. So for example, it can receive energy from electricity. It doesn't have to be heat. But basically, if you heat this thing up, then and it receives the right amount of energy, then it has the possibility to the electron has the possibility to move outside of its ground state. When the hydrogen atom is in its ground state, psi is essentially 1s, so the wave function is essentially that, the 1s orbital. And E is essentially the energy of the 1s orbital the potential field of 1 proton. We, of course, know that electrons can be excited. However, they do not contribute much to the energy of a sample of atoms or molecules for two reasons. Number one, it takes quite a bit of energy to do that. So, and under ordinary conditions, most atoms and molecules are in the ground state. And number two, even if you are able to promote an electron, its lifetime in that excited state is smallish, right? So it relaxes pretty quickly. So typically, if you're looking at electronic energies of a sample of atoms or molecules, they're pretty much going to be the ground state energies. Okay, so that is probably longer than I wanted to talk on this topic, but I had fun doing it, but I'm going to end there and move on later to the next crash course.